Okay,
Start.
let's start. Thank you very much, everybody. We are gathered here today for the third session on the ThorCon training and workshop. And today we have a special guest coming, Mr. Lars Jorgensen, CEO of ThorCon, and Dr. Manuele Afiero from Milano Multiphysics. Because we are so this is a very special session. So without further ado, I'd like to give the floor to our trainer, Professor Kun Chen. Please, Professor Kun.
Thank you very much, Bob. And I'd like to welcome every one of you to this workshop. And this is the third week. In the past 2 weeks, we have introduced the MSR in general and also the ThorCon 500 design in general. And this week, we're going to get into the neutronics and the thermohydraulics of the core, which is the topic that a lot of people here are interested in. So we got two guest speakers here. First one is Mr. Lars Jorgensen, and he's our CEO for ThorCon US. And Lars is going to introduce a little bit history about the evolvement of the ThorCon core, because a lot of people here have seen the several versions of the old ThorCon core, and Lars is going to introduce the improvement and the reason behind those improvements, and followed by Lars' talk, and we're going to introduce Manu, and he's the expert in neutronics and thermohydraulics. He's got education from Politecnico de Milano and the University of California, Berkeley, and he's been our main core physics and thermohydraulics guy for the past several years. So I'm very much looking forward to the interesting presentation that he's going to give us this morning. If you have any questions regarding the presentation, you can either raise your hand or leave your question in the comment. We'll be watching for that, and after the presentation, we will answer those questions one by one. And so next week, we're gonna have the a presentation about the operation of the power plant, followed by the 5th week on off-gas instrumentation control and radiation protection. And the week 6, we're going to introduce the design and the safety assessment. So a lot of questions you may have today, we still get a chance in the next several weeks to talk about that. So without too much words, I'd like to give the floor to Lars.
Okay. Yeah, Manu, if you could show slide 5. Okay, so you can see in this, on the left part of the slide, you can see the design that many of you have seen, where the heat exchanger is running vertically adjacent to the core, and the core is taller than it is wide. At that point in the design cycle, we had not been talking with the graphite vendors, but had been running off of what Oak Ridge had planned to do. And what we have found is that what Oak Ridge assumed would be able to be done was not feasible with the graphite vendors without spending a lot of money, and in fact, much of it wasn't feasible at all. So making isostatic fine flour graphite that was 5 meters tall simply is not feasible and will not be feasible. That drove design changes. On the right side, you can see how it is now it is wider than it is tall. It's roughly the same volume, but in order to meet the restrictions of the graphite, we had to make the pot shorter, because we cannot make graphite logs as long as we like. That meant that in order to maintain the volume, we had to make it wider, and that pushed the heat exchanger to be completely above the above the reactor core. That has some good side effects in that now natural circulation is much stronger, and the heat exchanger is U-shaped, which is better for thermal expansion of the tubes in the heat exchanger. But it has a downside in that now we have more salt volume outside of the core. The details inside the core are still being resolved as we're working with the graphite vendors to see what can they really manufacture in the volumes we need. But the differences are details in the graphite manufacturing process. So we're settled down pretty much on the shape of the core. Okay. I should introduce one other thing, which is the details of the interior of the core when they are what we're actually going to be built will need to be classified 810, which restricts us to people who've been approved to see it, or organizations that have and that understand their responsibilities that go with that. And so I can't get into the fine details of the interior of the core in this meeting. Okay, I think that's it for me. I think Manu, the ball's in your court.
Okay, thank you very much, Lars. Kun, feel free to guide me. I think we can just have a look at the main components and then look at the neutronics and thermohydraulics behavior of the reactor. Please stop me if anything is not clear or for any question. The main components involved in the core behavior analysis besides the core are the pump, the heat exchanger, and the loop and the valves, along with the drain tanks. These are the components involved in what we are looking at today. The can life is limited by the graphite degradation. The damage in the graphite is induced by a combination of high energy neutron irradiation and high temperatures. Usually the behavior of graphite is to first shrink in size and then swell or expand. This is related to the relocation of defects and vacancies and interstitial in the lattice of the graphite. This lets the replacing of the graphite and so of the can. We can skip the main values for the reactor and move straight to what happens inside the core from a neutronics and thermohydraulics point of view. As Lars was pointing, this is not the latest version of the logs. These refer to a previous version, which is presented as a result in the present presentation. The numbers might be different, but all the phenomena and general behavior applies to the present reactor. So this is a perfect case study to show the behavior of the ThorCon reactor. This hexagonal log is not any more of this shape in the present design, but this hexagonal log is constituted by graphite acting as moderator in green and by fuel passages. Here the fuel passages are small gaps between different slabs. In the present design, there are gaps and holes, but the behavior is the same. The fuel is heated through its path along the 3-4 meters logs from bottom to top, reaches the maximum temperature, is heated due to mainly fission, and graphite is also heated by gamma and neutron irradiation. So the salt, which is the fuel, acts also as main coolant for the graphite. A variable fraction of the heat, let's say around 5%, is released in the graphite. The temperature of graphite increases the irradiation damage due to neutron at high energy. So we are interested in keeping a low graphite temperatures. The core is constituted by the main logs and refractor logs. This is still the same in the present design. The thermal expansion of the salt and the heating of the salt causes two different feedback. The sum of the two leads to around -2 ppm per Kelvin. The Doppler broadening is, as an usual reactor, related to the broadening of the resonance in fertile materials, namely uranium-238 and thorium-232. The broadening of the resonance in the resonance region increases the probability of capturing and significantly reduces the chance of neutrons to be thermalized and producing fission. The fuel thermal expansion has itself two different effects. By expanding, the salt reduces the effective density of salt inside the core. This increases the probability of leakage by a smaller amount and also increases the effective moderation in the core by reducing the effective fuel to moderator ratio. This might have a positive effect. Nonetheless, the sum of the heating effect on salt is always negative and around -2 ppm per Kelvin. There are some variation depending on the fuel to moderator ratio and depending on the specific heterogeneity, but that's effectively an average value for the core. Also, graphite has a reactivity feedback. The effect of graphite heating is related, it's twofold. The first effect is related to the thermalization of the neutrons that when the moderator is exposed to neutrons leads to an effective equilibrium between the thermalized neutron and the temperature of the graphite carbon lattice. Heating the graphite shifts the Maxwellian distribution of the pseudo-equilibrium of thermal neutrons, and this moves effectively the thermal spectrum of the neutrons. Also, the graphite expansion, let me go back to these slides, effectively pushes a little bit of salt out of the core. Both effects are summed up and lead to a negative overall effect in the present design. And again, this is a reasonable number which undergo minor changes depending on the specific core configuration. We're going to have a brief look of the main components of the variable in the analysis of the core. And I'm going to use this video. Please let me know if it's clear enough to introduce the main phenomenon in nominal operation. Again, this is published materials. You can find this in the ThorCon website. Does not refer to the latest design. It's the hexagonal log design, but serves very well the purpose of describing what happens. Let it load and let me know if you can see it. Sorry, it's coming up. So this is the distribution of the fission power. Let me pause for a while. In common reactor of pseudo-cylindrical shape, we expect the distribution to follow a cosine towards the z-axis and a Bexel function toward the radius. And this is what we have. At the center, we have the peak of the power, and we have lower power density in the bottom, in the top, and the radial periphery. In this specific design, the control rod were inserted in the center, and there it is where you have a reduction of the power distribution. In the present design, the control rod have moved, but a similar behavior is still seen. So we have a standard distribution of power. The fission power heats the salt, and this is the fission power in the salt in the gap. And this is used to calculate the temperature distribution of the salt. And so the temperature distribution of the salt is different from the power distribution itself, because we have the power to precisely choose the flow rate in each of the hexagonal logs, or the flow rate in each of the present-day design log. This is done as much as we can to flatten the temperature distribution and to have an outlet temperature which is as much as possible uniform radially to have a uniform outlet temperature of each log equal to the maximum fuel loop temperature. And this is what is shown here. For the outermost periphery, the maximum temperature is not reached even with the minimum allowable flow rate. So we have a smaller amount of salt exiting the core at a slightly below temperature compared to the maximum. The graphite temperature, as we were saying, is determined by the temperature of the salt, which is cooling it, and the amount of photon and neutrons hitting it and eating it up. So basically, the graphite temperature is obtained starting from the local salt temperature plus the amount of energy released divided by the effective heat transfer coefficient between the graphite and the salt. The design of the specific log is a trade between optimal moderation and optimal heterogeneity, and being able to cool enough the graphite. Once again, too much of high graphite temperature results in a faster than acceptable neutron damage, which consists in shrinking and then expanding again due to the defects and relocation movement. But we can analyze the graphite temperature in a similar way. The analysis presented here, even though they refer to a older design, reflects exactly what is the analysis that ThorCon is conducting on the present day core based on the Monte Carlo code Serpent and the multiphysics tool OpenFOAM to keep track of the salt and graphite temperature along with the neutron flux. I don't know if this video helped a little bit understanding what is the main part of the flow, the main temperature distribution, and the power distribution. Please let me know if anything is not clear, so that we can assume this is the understood behavior and move on. I don't see anything in the chat, so I go ahead.
Manu, usually
please.
people ask after it's over.
So, sorry about that.
Yeah.
Copy that. Thank you very much. Sure. So this is the core, of course, the main component of the primary loop. Let's have a look of the other component as well. The pump and the header tank are located above the core. So this is the pump, and it serves the purpose of moving the salt around the core. The circulation time, again, is changed in recent design due to more accurate estimation of the salt capacity, but let's say is in the order of 10 seconds to 15 seconds recirculation time. That means that we have to move around more or less 1 cubic meter of salt per second. So that dictates the requirement of the pump. And the header tank is placed again on the top part of the primary loop and provides surface area to facilitate the removal of gas from the salt. So basically, it provides a space for salt to gas interface. There is a continuous purging of helium, currently set at 2 liters per minute. We will see in a few slides the path of the off-gas system and the behavior of the decay in the different components. One of the main reasons for this is the continuous removal of xenon-135. As you know, xenon-135 is a huge neutron absorber and has a large impact on a uranium-5 fueled thermal reactor. In solid fuel reactor, your xenon-135 is bound to stay within the fuel, and the reactor operation, especially in changing power, is dominated by the behavior of these nuclei. We'll see in a while that this effect is much reduced in the ThorCon reactor due to the fact that the header tank is capable of effectively removing it from the fuel. Part of it is absorbed in the graphite. The exact amount that will be absorbed in the graphite depends on the specificity and porosity of the graphite is not known perfectly right now. So different hypotheses on the xenon-135 intake into the graphite are being made and included in the reactor analysis. Besides effectiveness on the reactor operation, removing gaseous fission product has a huge effect on the reduction of the source term in case of accident. The primary heat exchanger, as mentioned before by Lars, has moved from the side of the core to the top. The primary heat exchanger is made by a U-shaped shell and tube heat exchanger. The adoption of twisted tube is due to the enhancement of the heat transfer coefficient on the shell side. The fuel salt stayed in the shell side and the secondary salt stays in the tube side. In case a leak, we'll send the secondary salt in the primary loop rather than the opposite. Also, the management of the decay heat is facilitated by having the fuel in the shell side. The freeze valve is a feature that has been adopted since the beginning of the era of molten salt reactor. In a simple word, the freeze valve is just a pipe that is occupied by solid fuel that has been frozen and constitutes a barrier for the flowing on the molten salt above it. The freeze valve acts passively as it is continuously refrigerated and cooled by a flow of helium that keep the plug of salt cooled. As soon as this active flowing of helium is interrupted, either voluntarily or due to the stopping of available power, the heat in the heat capacity surrounding the valve starts to flow through the valve to the plug of solidified salt until the salt melts and the valve is opened. The design of the valves is taken directly from the Oak Ridge era. So the operation of this valve has been already tested in real application and determined to be reliable and replicable in the sense that the time for the opening of the valves might not be known at the accuracy of the second, but is can be estimated and is reliable in a reliable way. The number of valves are selected in order to have a draining time acceptable for the transient that are being studied. In the present design, there are 4 valves that copy the Oak Ridge design here. This picture, again, all this is public material, shows in the detail the design of the valves. This is the specific section where the solid plug is present. Once the valve opens, due to the absence of active helium cooling, just by gravity, the salt drains in the drain tank. The drain tanks are the tanks below here. We are not showing presently in this picture the lines that delivers the flowing salt from the valve outlet to the group of drain tanks. But the drain tanks are those cylinders. The drain tanks are the green vertical cylinder partially shown here. Once the valves are open, The drain completes in approximately 10 minutes. The draining time depends mainly on the amount of salt, the viscosity of the salt, and the density of the salt. These physical parameters have little impact, though, on the time of the draining, which requires around 10 minutes to complete. This provides a strong safety feature for the drain. I can show you a volume equivalent picture showing what happens. First, the drain, the other tank. Let me go back a second. This is a volume equivalent. This is not the core. This is a cylinder who has the same volume of the salt contained on the core. And this is for the heat exchanger in a similar way. At the present design, the heat exchanger was still, at the design showing this picture, the heat exchanger was still vertical. First, the other tank is emptied. Then the pipe completing the primary loop below the valve. Then the primary heat exchanger is emptied. And finally, the core empties. These all happen in approximately 600 to 700 seconds. And the flow of salt is stopped after 700 seconds, and all the salt is in the drain tank. The salt in the drain tanks evacuates heat mainly due to radiative heat transfer. The drain tanks are surrounded by steel walls that are effectively cooled and submerged in water. There are walls outside and inside of the drain tanks group. So effectively, the drain tanks can see cooled wall on both sides. The view factor from the drain tanks to the cool steel walls is rather high, higher than 50%. So the drain tanks release heat mainly due to radiative heat transfer and can grow rapidly. The heat delivered based on the maximum temperature of the salt. This refers to a previous design, but with the current design, the difference are minor and related only to geometry, not to the behavior. As you can see here, the peak temperature is reached in the salt in the drain tank just below the top free surface of the salt due to the convective movement of the salt within the drain tank. The hot walls radiate heat towards the surfaces of the steel walls cooled by circulating water. It is expected that water reach boiling temperature, and nucleate boiling increases the rate of heat removal. Not depicted here is the circuit of the water going and steam going towards the pond and releasing heat in the pond that provide a long time heat capacity, and finally to the air in the following time. Going back to what happens during the draining, we can see that another effect of the draining is, of course, the reduction of the reactivity of the core. Let me zoom a little bit this picture. You can see here the reactivity of the core during the draining. At this time, the draining line reaches the elevation of the core, and we can see that the core starts emptying. This slowly but steadily introduce negative reactivity that definitely stop the power in the core. Of course, in most accidental scenario, the reactivity of the system during a draining, it's already severely negative, and the power has stopped due to the introduction of negative reactivity due to control rod and to the negative reactivity feedback due to the heating up of the salt. So in most scenarios considered, the negative reactivity introduced by the draining of the salt is not required to shut down the reactor. Once the salt is drained in the drain tanks and they are effectively exchanging heat with the cold walls, we see that at the beginning there is a rise of the temperature due to the decay heat. You can see the decay heat in this line reading from the right. This is the decay heat in megawatt, and this is the time in minutes after the shutdown of the core. So up to several minutes after the shutdown, the power is in the megawatt order of magnitude, and the heat has to be released to the cold wall. This requires a rising of the temperature of the salt and so the temperature of the drain tanks. The main sizing criteria is now the creep damage of the drain tanks. The stress level is relatively mild, but the temperature follows this behavior, rising at the beginning due to the higher decay heat and then slowly going down as the decay heat decreases. The calculation of the creep lifetime is done based on an available correlation for the creep that relates the maximum stress or the von Mises stress and the temperature. The creep is calculated both in the position where the stress are maximum and the position where the temperature are maximum. And we see that in any relevant scenario, the creep damage in the drain tanks is relatively mild, well below 1% of life. This is a sketch view of the drain tanks, and one of the questions that has to be answered is the possibility of criticality of the drain tanks in case of a leakage that introduces accidentally water in the system. This is an unlikely scenario, but nonetheless, the reactivity of the drain tanks full of salt, also considering the mixing with the makeup fuel, is way below 1. So there is no possibility of criticality, even in case of flooding of the entire space surrounding the drain tanks. Also, the fuel makeup tank is this one. This is the tank that contains the fuel required to feed the fission reaction for the 4-year operation. While we are here, we can also see the thorium makeup tank next to it that can be used to reduce the reactivity of the system as other means to reduce the reactivity of the system. So also the fuel makeup tank, as you can see, is relatively close to the core. So it has, it sees a relatively mild flux of neutrons leaking from the core. This flux of neutrons induces fission in the makeup tank. The criticality of this component is very low in any foreseeable condition. Nonetheless, the fission heating due to the fission occurring in the fuel makeup tank might induce a temperature beyond what is desirable for the component, and so this component is shielded by steel or porous steel or boron carbide plates to further reduce the amount of neutron leaking the core and reaching the fuel makeup tank, inducing fission in nominal operation. One of the main effects that distinguish circulating fuel reactor with respect to solid fuel reactor as far as the neutronic analysis is concerned is the change in the effective delayed neutron fraction. The effective delayed neutron fraction is the fraction of neutrons that is not emitted promptly during a fission, but is emitted with a certain delay, usually through the neutron emission decay of one of the fission fragment or one of the fission product following the decay after a fission fragment. Uranium-5 sees approximately 0.607% of effective delayed neutrons. The term effective relates to the fact that we are not counting the physical number of neutrons emitted with a delay, but we are correcting this physical number with a value related to the fact that the different emission spectra plays a different role in the moderation process, and so the delayed neutrons might have a slightly higher or lower effectiveness in producing the fission. So at zero flow rate, the ThorCon reactor will see a 650 PCM of beta effective. PCM is 10 to the minus 5. This is a standard value for uranium-5 fueled reactor and very common in thermal reactor. Nonetheless, when the fuel is circulating, part of the delayed neutron precursor that are created during a fission event are transported through the core and outside the core before they are able to decay. So a large fraction of delayed neutrons is emitted by the delayed neutron precursor, not in the place where they were created, not even in the core sometime, but they might be emitted in the pump, in the other tank, in the primary exchanger, that is, in places where they are not able to contribute to the fission chain reaction. While this has a negligible effect on the neutron economy, Sure, I go back to slide 12. There is a question in the chat elaborating more on the axial distribution of neutron flux and power density on slide 12. So this is the power distribution. The profile shows a much higher values in the upper part of the core, which may not be beneficial for common reactor design. No, there is no shift towards the top of the reactor. From what we can see in the picture, is fairly symmetrical between the bottom and the top. Indeed, there is a slight shift toward the bottom because the cold salt in the bottom side has, let's say, a local higher reactivity, in the sense that the higher density there and the lower temperature result in total in higher local reactivity, whereas the slightly higher temperature on average on the top of the salt result in slightly higher Doppler effect and negative reactivity. Since the size, the neutronical dimension of the size are not too large, the imbalance between the top and bottom is relatively mild. Yes, that's the temperature distribution. I believe you were referring to this one, which is the temperature distribution. I'm sorry, I'm not able to put full screen due to the problem in my Linux system, but yes, this is the temperature distribution, which of course is unbalanced towards the top, but not the power. The power is fairly symmetrical, and if any imbalance, the imbalance is toward the bottom. If this answers the question, I go back to the presentation. Sure. And so the effect on the neutron economy of the delayed neutrons leaving the core is rather mild. Say we are losing 0.03% of the neutrons due to this move. On the other hand, it has some effect on the control of the reactor. This is related to the fact that we are finally having an effective delayed neutron fraction, which is slightly lower. In particular, at nominal flow rate, the effective delayed neutron fraction reaches value of around or below 300 PCM. This number should not pose any problem. They are actually not much lower than what we see in solid fuel fast reactor in which the contribution of plutonium isotopes and minor actinides severely decreases the delayed neutron fraction. Nonetheless, what is peculiar is not the small value of the effective delayed neutron fraction, but it is the fact that the delayed neutron fraction effectively depends on the flow rate. So since it is possible, in principle, to operate the reactor with a variable speed pump and a variable circulation flow rate, even if this is not in the present control design of the ThorCon system, in that case, we will have to take into account that reactivity beyond the reactivity feedbacks due to temperature is changed and introduced due to the different flow rates. And effectively, if we stop the circulation, either voluntarily or by accident, around 300 ppm of reactivity, or slightly above that number, are introduced due to the fact that the delayed neutron precursor that used to decay in the primary heat exchanger or in the piping, or even in the periphery of the core, are now decaying inside of the core. So effectively, once we stop the pump, keeping in mind that there is inertia that keeps the flow circulating for some time, the reactivity is inserted corresponding to the difference of the reactivity of the difference in the beta effective between the static condition and circulating condition. This is a well-known feature of molten salt reactors studied since the Oak Ridge era. So we just have to take this into account during the analysis and the design of the control system. It might be a little tricky for all of us coming from solid fuel reactor experience. So if you have any question on this specific issue, I will be happy to discuss more in detail. Otherwise, I move on. Let's analyze, see if anyone has a question. Otherwise, I believe we do that at the end. Let's analyze what happens with xenon during transit. The fact of xenon as a strong absorber, I apologize for not being able to put full screen, so I'll try at least to put the picture at the maximum size I can. Of course, the ThorCon will distribute the presentation at high quality and resolution, so you will be able to look at this. Let's imagine a change in reactor operation with the reactor, ThorCon reactor that has been operated for in steady state for a long time, let's say for 15 days at full power or 100% nominal power. In this case, the xenon in a solid fuel reactor would reach a well-known level that just depends on the amount of iodine-135 that is produced as fission fragment and fission product decay chain, the amount of xenon-135 that is captured by, that is destroyed by neutron capture, and the amount of xenon-135 that naturally decays. In circulating fuel reactor, and specifically in the ThorCon reactor, where the header tank plays the role of removing gaseous fission product, the calculation of the effective content of xenon-135 is more difficult. In particular, it has to be defined and confirm the effectiveness of xenon-135 removal through the surface gas to salt surface interface and the amount of xenon that reaches the graphite pores. This is not perfectly known at the present moment. And nonetheless, we can make hypotheses and assume two different scenarios. One in which we have a very fast effective removal rate, and one in which we have a lower effective removal rate. In both cases, after 15 days of operation, xenon 135 reaches an equilibrium value. We are calling the xenon 135 mass as the effective mass of xenon that will be present in the salt, giving the same reactivity effect. If part of the xenon is not present in the salt but into the graphite, its effectiveness is slightly higher due to the slightly higher thermal flux there. So let's call this the effective xenon 135 mass. Let's see what happens when we drop the power virtually instantaneously at day 15 from 100% to 50%. So what happens in this case, as you can imagine, is that the production of iodine is dropped from the equivalent equilibrium values at 100% to the 50% value. And so slowly, the fraction of iodine reduces. And let's assume for both cases two scenarios. One in which we keep the removal rate constant. Let's start from the orange line here. So if we drop the power instantaneously from 100% to 50%, and we keep removing xenon with the same effective rate we were assuming for the steady state operation in 15 days, slowly the system adapts to the new level of xenon decay rate coming from a reduced level of iodine production. You can barely see a slight increase here at the beginning. This is due to the minor fraction of xenon atoms that are removed by neutron capture. At the beginning of the change in power, the xenon 135 level is almost constant because it has not changed its equilibrium value at all, and the fraction of xenon removed due to neutron drops by 50%. So you can barely see this increase because in the ThorCon reactor, the amount of xenon removed by neutron capture is very small, almost negligible. So in the case where we have a medium effective removal rate, for example, meaning that a significant fraction of xenon is indeed absorbed in the graphite, if we keep removing at the same rate, well, slowly, with a time constant related to the decay of iodine into xenon, we will adapt to the new value that is roughly more or less half of the equilibrium value of the xenon concentration at nominal 100% operation. On the other hand, if we adapt our removal rate, so in a simplifying term, the amount of salt flow that is flown in the ether tank or exposed to the salt to gas interface, if we halve it effectively, after we reach equilibrium, we will go back to the same xenon equilibrium concentration that we had before the change in power. So in a simplified way, regardless of the possibility of removing fast or slow the xenon, so regardless of the effectiveness in removing the xenon, we can assume that the ThorCon reactor, if it's possible to tune and change the effectiveness in removal in response to a transient, we will always be able to maintain a net zero reactivity effect. Let's analyze this case. This is the reactivity change due to the change in xenon effectiveness. And this is the net reactivity effect due to xenon absorption. This is the fast effective removal rate. So the xenon effect is very small, below 100 ppm, compared to the 1000 ppm of, for example, a PWR or an HDGR, for example. Well, in those cases, if I stop if I keep on removing xenon at the same rate at day 15, the concentration of xenon, as we were seeing in this picture, drops. Sorry, the mass of xenon increase if I move to 50%, whereas if I keep removing with the same rate, the concentration drops. And in the two cases, I will either slightly move to half of the effective reactivity loss, or have a peak at the beginning and then go back in a few days to the same equilibrium value. What we are implying with this description is that if the ThorCon system is capable of tuning constantly the removal of xenon, depending on the time constant for in the graphite to migrate back to the salt, we are capable of ensuring an almost zero reactivity transient. So the effect of xenon can be managed. It is very small to begin with, and then it can most probably be handled regardless of what will be the effective fraction of xenon that goes into the graphite. This is one unknown right now. It is not exactly known the fraction of xenon that will permeate in the graphite. The graphite is treated in a way to close as much as possible the pores, but even in case part of the xenon goes into the graphite, we know for sure that its effect will be much, much milder than solid fuel reactor. And we expect no forced shutdown period after an accidental change in power due to the xenon peak like we have in other reactors. Again, if you have any question on this, be happy to answer. This is the path of the off-gas system. So as we were saying, the fuel is moved to the header tank, where there is an interface between the fuel liquid salt and the 2 liters per minute of helium that flows in the system. This offers a path for the fission gases to move from the salt to the gas. After leaving the header tank, well, bear in mind that if we have 2 liters per minute, and here we are talking at about 4 cubic meter, the time required for the salt to leave, for the gas to leave the salt might be very quick, but the time required for the gaseous fission product to leave the header tank is quite large. So a lot of decay happens inside the header tank, but outside of the core. So the non-gaseous daughter of gaseous fission products, in most part, do decay inside the header tank and are go back to the salt where they stay as soluble fission product. Once the gas leaves the header tank, then it goes to the OGR. Each OGR is divided in 4 sections, effectively introducing a plug flow that avoids the mixing of the gas inside the OGR and increases the effective residence time. So in this case, again, the decaying fission products will release non-gaseous daughter of gaseous fission products in the OGR that will deposit on the surface, where they can easily radiate decay it outside. The gas follow a rather long path. Bear in mind that most of the decay heat by far is released in the header tank and then in the first OGR. And then the salt, the gas follows a long path to ensure that all the fission products are captured before going back and recycling the helium back into the system. I will move to decay it unless Lars or Kun instruct me to follow the path of the gas up to the charcoal bed and the cold trap.
The one thing I would point out on this is that the header tank OGR1 and OGR2 are inside the can. And by the time that we've gotten out, leave OGR2, the radioactive gases are noble gases and their daughters are not radioactive. So if you were containing all the radioactive daughters inside the can, and the only thing outside of that is noble gases, which are ideal dispersal and have almost no residence time in anything. If you breathe them in, you'll breathe them out again right away. So the major part of the off-gas danger is kept contained inside the can.
Thank you, Lars. So there's a question. It might have been misleading discussing about the negative. So the question is related to the fact that reactivity due to the drain is introduced slowly. I apologize, it might have been misleading talking about negative reactivity due to the drain. The main purpose of the draining is not to introduce negative reactivity. The reactor itself is very effective at bringing the reactivity to the negative sides and the power towards zero due to the reactivity feedback. So in case of any of the postulated accident, if the temperature of the salt and the graphite goes up, the reactivity goes promptly down. There are also considered contra road, and this effectively shuts down the reactor. On the top of that, draining also introduces reactivity, and this is what was being mentioned, but this is not the main used to shut down the reactor, even though it does bring the reactor to severe negative reactivity. So the main purpose of the draining system is to have a place where the salt is passively cooled for a long time, I will say indefinitely long time, through to the passive natural circulation of the salt inside the drain tanks. Then the passive evacuation of heat from the drain tank to the cold wall due to the radiative transfer, a phenomenon that increases in surfacial heat transfer rate very steeply when the temperature rises, and then the heat is ultimately evacuated due to the natural circulation of water and water steam mixture in the cold wall to the silo up to the pond. That's the main purpose of the draining. I apologize if I misled you discussing the negative reactivity during the training. Yeah, Lars, please take this.
We're done. You can keep on going where you're going. I think everybody caught on to that.
So differently from a solid pure reactor, we have the advantage of being able to continuously remove the main source of radioactivity in case of accidental release. That is related to the fact that we can remove gaseous fission product. So this is we have a much reduced source there. But this is also implies that the decay heat is not only released inside the fuel. We are analyzing here the distribution of decay heat in the first few days after shutdown, as in the fuel salt, in the cold trap or primary heat exchanger, where the noble metals, or let's say the insoluble fission products, might plate out. The other tank, as we were seeing before, and the first OGR. The other off-gas components have very small decay. Here in the OGR, we are summing up the four main section that behaves as plugged flow. So some are above 1, 2, 3, and 4 section, and also the OGR, but considering not the gaseous volume, but what has been plating out due to decay. As you can see, of course, most of decay is inside the salt, but also the decay heat rate in other component has to be analyzed and taken into account, as it might reach values above 1 megawatt in some component for the first few minutes after shutdown. This is the case for the other tank and the PHX. Here we are assuming that all insoluble fission products are plating out. This is an extremely conservative assumption from Oak Ridge era analysis. Not all the noble metals were plating out in the PHX. Nonetheless, this poses the necessary requirement to consistently sizing the decay heat handling for this component. As you can see, the decay heat in the OGR is rather large, but fairly in the manageable region, well below 1 megawatt. We are starting at less than 100 kilowatt and reaches very much lower values within 1 day. If you have any question on the decay, please let me know. Another advantage of the present ThorCon design is that right after an accident, let's say a loss of flow, the decay heat is released in the form of, well, mainly beta decay that release locally energy as brainstorming from slowing down of the electron, and then as photons, both from gamma decay, mainly from gamma decay, that might travel into the fuel and reach also graphite. Depending on the time after shutdown, the average energy of the emitted gamma changed significantly, but let's say that roughly up to 40% of the decay heat that is released in the core after shutdown does not go directly into the salt, but is released inside the graphite. This, along with the large heat capacity of graphite, keep in mind that graphite might be between 90 and 95% of the volume of the core, and as rather large heat capacity, the heat capacity of the graphite might absorb a large fraction of the energy of the decay heat in the salt during, for example, the 10 minutes between an accident and the effective opening of the freeze valve. So this plays an important role in further reducing the heat load in the drain tanks. And this is a twofold reason. One is just the heat transfer between the salt that is heating up and the graphite that was initially at a higher temperature with respect to the salt, but soon after that is surpassed by the salt, which sees a larger decay heat, and by the fact that some of the decay heat goes straight into the graphite. This proves very effective in reducing the maximum peak temperature reached by the drain tanks after an accident. Oh, thank you, Kun, for clarifying. Um, Lars, do you want to take this one much better than me, I believe?
Okay. So if we start with the can A, we have our primary loop that's filled with fuel salt and is barely critical. And then we add roughly 1 milliliter per minute of makeup salt. So that adds up to about 2 cubic meters over 4 years. So that's the purpose of the makeup tank. We do not have burnable poisons. We do not put thousands of PCM of excess reactivity into the reactor at the beginning. Instead, we add fuel a little bit at a time. It is a closed feedback system. So as opposed to a solid fuel reactor where you need to know very precisely how the fuel burns up in many different locations and how it will behave over a full 6-year period because it's all open loop. Here we're closed loop. So we can measure the temperature and say, we're a little bit cold, we need to add, or a little bit cold, so let's add less makeup salt. Or it's a little bit hot, the reactivity is a little bit low, we want to add more makeup salt. So you can continuously adjust how much makeup salt you're adding. That can compensate a lot for uncertainties in the design. So it circulates in can A for 4 years. Then we drain it and it'll be in the drain tank for 2 to 4 weeks. During that time, we are doing the major maintenance action, in particular for the turbines. But at the same time, you do all the other maintenance actions you want to do. Then we will transfer the salt over to can B, where it'll operate for another 4 years. And there's a makeup tank in can B that will feed the additional makeup as we go. And at the end of that time, it gets drained into its drain tank. And we have another maintenance cycle for the turbine. After it's been in there for a couple of weeks, it is now cool enough that we can transfer it to what we call the holding tank. That is very similar to the drain tanks in the sense that its cooling mechanism is to radiate to a cold wall that contains water, and that water naturally circulates to the pond water, the same pond water but with a separate radiator circuit. It can stay there anywhere from 6 months to several years, but we'll want to transfer it out of the holding tank and into the vault before the next drain event. The vault is a series of 6 cylinders that are very similar to the other tanks. They're larger and taller. They're 20 meters tall. But instead of using water cooling, they have air cooling. That means that their cooling capacity is less, so we don't want to transfer to the vault immediately. But this is our version of dry cask storage. It consumes about 5 meters of the hull length, and it'll provide us with 80 years worth of spent fuel storage. So we can move it all the way into dry cask storage and do all that motion inside double-walled pipes in the basement area that is secured and safeguarded, and done with pumps. So none of this involves people being in the neighborhood. When the permits are finally in order and the facility's built to do any kind of processing and final disposal, then we remove it from the vault and ship it to the final disposal site. Based on experience in the US, that's very hard to predict when that will be finally ready. So we want to have enough storage in place for lasting the full life of the power plant. We would like to do at least processing to remove the uranium before we put it into final disposal. The uranium that's in there still is very valuable. It still has significant enrichment on the order of 9%. So it's valuable fuel. And we probably also will want to extract the beryllium because the beryllium is also our next most expensive component in the fuel. Any further processing is much more of a political decision than a technical one. That would be for one power module. There would be 2 such power modules in a ThorCon aisle in the typical 500 megawatt hull that you see in all the pictures. Okay. Next slide. Okay. Then I think that covers this.
Lars, there's a question from Dr. in the chat.
Okay. Yes, burn-up value. That gets a little trickier to define when you have both uranium and thorium in it. If you're measuring it based on thorium, you know what? I don't have those numbers off the top of my head. What I can tell you is that we use less uranium than a light water reactor. The thorium could be recycled. It doesn't get hurt at all by being in the reactor. The question comes down to what is the value of recycling it? Is almost likely that the cleaned fresh thorium will be cheaper than pulling thorium out of the spent fuel, but it could be done either way. Equivalent value of burnup. I did calculate this at one time, but it's just not something that is terribly important to me, so I don't remember it. I'm sorry.
Could you maybe give it later on? Email me so I can share with the groups.
Okay.
All right. Thank you. So that's the end of the presentation. So question and answers, gentlemen, ladies. You can right away speak ups or write on the chat. Okay, from UGM. Okay, we have right away. We have from Almanso. From Almanso, is this, I think for Manu, yeah? When coupling the thermal hydraulics with the neutronic in the modeling MSR, what code do you use? How do you do burn-up calculation when simulating the two-phase flow in the reactor? Okay, Manu.
Yeah, so there are 2 questions in this one. So I'll take the
Yeah.
first one first. We use a specific set of tools based on Serpent coupled with OpenFOAM. Serpent is a Monte Carlo code developed at VTT Finland. It has specificity that makes it very suitable to do this kind of analysis, namely delta tracking, which implies that it can be coupled with finite volume codes very effectively. In our case is the multiphysics code OpenFOAM. Serpent can be coupled directly in the sense that given a reactor geometry, it is straightforward to take the density and temperature distribution of a material, let's say salt, inside the core from the solution of a thermohydraulics code and input towards that code the power distribution, which is exactly what we do. We solve Monte Carlo neutron transport to find the power distribution. We use the thermohydraulics code to find the temperature distribution of the salt given that input power distribution, and we feed back the temperature and density distribution for the salt and the graphite, and then it's just a matter of iterating. Let me know if this answers the question while I move to the second one. How do you do burn-up calculation? Well, burn-up calculation in molten salt reactor are effectively hard per se, because there is, well, more than two phases. There is a lot of submaterial with movement of isotopes from one material to the other, and even outside of the core. We started developing a specific code based on Serpent in 2013, and now all the features required to model molten salt reactor, namely movement of isotopes from one place to another, are directly available in the latest Serpent version. So the Monte Carlo code Serpent has burn-up capabilities with the solution of the exponential matrix, the Chebyshev rational approximation, and recently as included in the standard version, no more in the extended developed one, the possibility to move material around to simulate even reprocessing, but in our case, gaseous extraction, noble metal plates out, and feeding of makeup fuel, and if needed, also of thorium. Does this answer the question, Mr. Almanzo?
So there from Dr. Siddiq, the next one, how quick the opening time of freeze valve?
It's around 10 minutes, and this is taken from the Oak Ridge experience, and then is around again 600 to 700 seconds, let's say 10 minutes more to fully drain the primary loop.
And follow-up question there, slide field management.
I'm part of it.
Like,
Yes, in fact, all but 2 cubic meters of the fuel from can A will be transferred over to the primary loop of can B. So the limit on how often you can reuse the fuel is due to trifluoride solubility in the salt. The trifluorides consist of uranium trifluoride and plutonium trifluoride, and then the fission products trifluorides. And as a group, the solubility is about 1% molar. And so we limit it to around 0.8% molar. As the fission products build up, the trifluoride content of the fuel increases. And so you want to retire the fuel before you get to that solubility limit, because it's hard to predict whether the plutonium is going to precipitate out first or the fission products, but we definitely do not want to have any precipitation of plutonium concentrating in some spot. So that's what limits the life of the salt to going 8 years, which would be 2 cans worth. We do have a little bit of extra salt because we added 2 cubic meters of makeup salt in the first year. So when we transfer it over to can B, we will have a couple of cubic meters of salt that we need to transfer to the holding tank instead.
I guess related is the latest question, question 3. Opening process of freeze valve is passive. What is active is keeping the valve closed and the salt solidify. The opening is passive.
So the freeze valve, the center part of it is kept cold with helium that's actively pumped. The salt adjacent to it is kept hot with electrical heaters. So if you lose the electrical heaters, if the temperatures are not in the right range, or you lose electricity, then the thermal capacitance of the salt adjacent to the frozen section will melt it completely passively.
I'll pick the previous one on the two-phase flow and gas bubble modeling in coupled reactor neutronics thermohydraulics. In fast molten salt reactors, we have developed specific tools to model two-phase flow and specifically the behavior of bubbles during postulated accident. In fast reactor, the average neutron prompt lifetime of around 1 microseconds makes the increase in power so fast that the effect on the compressibility of the fuel due to the presence of gas bubbles does play a role. Specifically in the European molten salt fast reactor, there is an active introduction of bubbles inside the core for different purposes. In that specific case, yes, there is a need to model as two-phase flow for specific accident. In the ThorCon reactor, there is no active introduction of bubbles. Actually, gas is continuously removed through the other tank, and it's a thermal reactor with millisecond lifetime. So there is absolutely no behavior related to explicit requiring explicit two-phase modeling. One thing is less bubbles in the core, and the other thing is being a thermal reactor with lifetime in the order of milliseconds. So two-phase modeling is explicitly required only when the compressibility effect becomes a dominant phenomenon, which is fast reactor with bubble injection. I hope that was clear.
I might further explain that as opposed to a boiling water reactor, the gas volume in the molten salt reactor is small. It's less than 0.5% of volume. So you don't need it in terms of the hydraulics. It's too small a volume to make a difference in the hydraulics.
All right, so there's a question from Professor Waris from ITB. And the last question, in the fuel cell matrix, the volume of the graphite is much, much bigger than the fuel salt. So the moderation become much higher. What is the impact on the fuel breeding? Manu?
The ThorCon reactor has a very good neutron economy and a rather large conversion ratio. It's not breeding in the sense that breeding ratio is not beyond 1, but the large fuel to moderator ratio and a good fuel mixture makes the conversion ratio rather high, also thanks to the large amount of moderator. It is not large per se in the sense that 5% fuel to moderator ratio is not incredibly small. So the 95% or 94% of graphite volume is not extremely large in the realm of thermal molten salt reactors. But yes, it does have a positive effect on the conversion ratio of the reactor without reaching breeding ratio of 1.
It was not a goal for ThorCon to make a thermal breeder. Our goal was to make a reactor that was cost effective, that could compete directly with coal, and that we could build without having to extend ourselves with a lot of R&D. It is a challenging endeavor to raise the money and to be able to build a reactor. So we have been trying to steer clear of doing too much new development and try to build it very much on what was already done for MSRE. And so we haven't tried to be a breeder. If you were a breeder, you also bring in a lot more concern over safeguards, and even GE with their Prism reactor had to veer away from touting its breeding capabilities because of the US pressure on what that might entail for safeguards and proliferation risks. So our goal was just to get a reactor up and running as soon as we can. We weren't trying to make a breeder.
All right, I hope that's clear, Professor Waris. Questions? Anybody?
I think there's an additional question here.
Yeah, from Alejandro. Right. During operation, because of the backup tank added fuel salt to the primary loops continuously, it is being...
I'll take that.
Yeah, okay. Please, Lars.
Okay. So yeah, as we add makeup salt, we do add volume of salt in the core. And there's two things that are happening. One is the graphite is shrinking in volume. And so as we add the makeup salt, it's compensating for the graphite shrinking. That happens during the first couple of years. Then for the last portion, the volume of salt that we're adding does exceed the capacity of the makeup of the primary loop. There is a weir, a pipe that goes from the maximum salt level in the header tank and goes down to the drain tank. So once you fill up enough, then the extra salt will flow down that pipe and go down into the drain tank.
I hope that's clear, Alejandro. So the next one from Ferry, this is quite long, very long questions. Manu or Lars, do you want to take this? From Ferry Wibisono.
So you say, which fuel salt are we using when we calculate reactivity? We calculate reactivity feedback at several stages. Basically, fresh fuel, 2 years old, 4 years old. You have to evolve not just the fuel, but also the graphite. And so we do that several times and track the change in reactivity over time and change in the reactivity feedback coefficient. Okay, Manu, you're going to need to take the next one.
Sure. So yeah, the reactivity feedback slightly changed during the evolution of the composition related both to the shift of the main fissioning isotopes that starts of the fissioning isotope that starts as entirely uranium-5 and then slowly drifts towards uranium-3 that is bred from the thorium present, and along with, as is perfectly stated in the question, with the accumulation of fission products. This effectively changes the spectrum, and so there is a change in the feedback coefficient. The change in the feedback coefficient, though, is relatively small and mild. So the change during the evolution of the fuel is somewhat of the same order of magnitude as the change between one configuration and the other. So we stay still around the -2 ppm per Kelvin discussed. I know if this answers the question, otherwise let me know. How do you consider that over the reactor life, the molten salt flow can form deposit and affect the molten salt flow process and heat transfer? Yeah, that's a very important question. It is known that non-soluble fission products, let's call them noble metals for simplicity, have a preferential deposit rate in colder areas. One of the cold area of the primary loop, as you might imagine, is the primary heat exchanger. So it is expected that a relatively large fraction of non-soluble fission products will deposit on the primary heat exchanger, thus effectively reducing the overall heat transfer coefficient. That is to be taken into account during nominal operation. It doesn't have an extremely large impact, but it has to be taken into account. On the top of that, in case of accident, those noble metals fission products are a source of decay heat in the primary heat exchanger, which might amount up to 1 megawatt of decay heat in the first minutes after the reactor shutdown. So that plays some role. I don't know if this answers the question.
Are there any further questions? Oh, there is.
Yes, it's from Pahendra. How is the process of startup reactor? How do we control reactivity to follow the load? Thank you. So, Manu or
Yeah.
Lars?
I can take this. I'll try to
Okay.
take this. So the reactor has a superior capability of load following in the sense that it is, thanks to its feedback, capable of changing the power load without major disruption at the temperature distribution in the main three loops. So there is the possibility to even vary the flow rate in the primary loop, but at present it's not envisaged as a necessary means of reactivity control. So the power following, the load following is operated just by varying the flow rate and the bypass in the intermediate secondary salt loop and the solar salt tertiary loop. So these effectively change the heat transfer rate in the primary and secondary heat exchanger, as well as in the steam generator and in the steam radiator, effectively allowing the reactor to quickly follow the load with several percent minute variation in the power without overshoot or extreme temperature variation. As to the startup procedure, that envisaged starting the reactor with a known critical mixture of salt, and then while monitoring the subcritical multiplication factor and adopting an external source of neutron monitoring the subcritical multiplication factor. And once the reactor is filled and subcritical, the filling of the makeup fuel from the makeup fuel tank is started up to reaching the criticality, at which point the reactor can be brought to critical at nominal condition. I don't know if this answers the question.
Lars, do you want to add to the explanation on Pahendra about the startup and the load follow? A lot of people been asking about that actually.
Okay, so load following is done by a combination of controlling the pump speeds and in particular controlling the bypass of the heat exchangers. So the core itself will naturally load follow. It'll naturally, if you take less power out, the temperature will rise, the reactivity will drop, and it'll settle back down to produce the power that you're pulling out. However, as we pull less power out, the heat exchangers get to be more efficient. And so when you reduce the power, you see the temperature rise as you go down the heat exchanger chain. And the bypasses are used to reduce the temperature rise so that we hold the steam constant temperature. The turbine is a sliding pressure design. So when you change load, you don't change the temperature of the steam that the turbine sees, you change the pressure. That allows us to change the power output much more rapidly because the steam system is at very high pressure, so it has very thick components, and you can't change the temperature very fast on those components because the thermal inertia of thick steel is such that you'll create internal stresses within the steel and you'll get thermal fatigue. So the goal in the design is any place you have thick steel is to have to keep the temperature constant. So we have simulated with our current plans up to about 10% per minute. but we have not analyzed all of the thermal stresses that occur. So as far as stable reaction, I can see the whole chain being stable up to about 10% per minute ramp rate. The requirement that I see using California's grid is around 0.2% per minute to do load following of the actual load. In California, we have an awful lot of solar, so we get an extreme event between 4 and 6 p.m. when the sun sets at the same time throughout the state. And so there we see ramp rates of about 1% per minute. So that's load following. Startup would be, you start with no fuel salt in the drain tank, in the primary loop. You want to have your shutdown rods lowered and then start filling it with fuel. The fuel should be targeted to be slightly under critical conditions when it is flowing. So you have the shutdown rods in place, you start the flow, and then you start gradually reducing or removing the shutdown rods. It takes about 10 minutes to fully remove the shutdown rods. The motors that remove them cannot go fast. And so during that time, you're observing the power and seeing that we are okay. If you start generating fission too early and you raise the temperature, the shutdown rods will drop again. Once you've got them all the way out and you're at flow, then you can add a little bit of makeup salt to bring you to full criticality.
Lars, the ramping rates, you said about 10% per minute. Is that equivalent to the performance of a gas plant? Is that equivalent, approximately?
Yes,
Well,
it is in the order of what is requested in Europe to gas plant, and actually in a connection demonstration, but not in standard operation. I don't know about other countries and specifically Indonesia, but in Europe and specifically in Italy, that's the maximum requirement for demonstration to be capable, but is never requested in nominal operation. So 10% per minute is...
It's a gas plant.
in some part of the world.
Yeah, I think.
yeah, it 10% per minute is really bragging rights. It's not something that's needed. In fact, in Europe, the maximum allowed requirement is 5%, and the nominal is 3%. So I want to be a little careful not to promise 10%. That's where I'm stating 10% now to say we're okay for stability of the reaction of the reactor and the whole chain. It doesn't oscillate, but I haven't evaluated the thermal stresses yet. So, but well, that's enough.
Okay, so follow up on that. What are the minimum level capacity that it can operate safely? You know, keeping with the load follow.
Right. So that's driven by the turbine. When you get to the low pressure, the final stage of the turbine, if you go too low, then you start getting water droplets forming, and the liquid impinging on the turbine blades will wear them out. So somewhere around 30 to 40%, 40% is for sure okay, 30% is pushing things a bit. Full power is where we would choose to set as a minimum power level for steady state operation.
All right, so 40% is you can maintain sustainably for steady state operation. That's about
Yes.
200 megawatts.
Yes.
All right, that's good enough. So as coming to the next questions from Dr. Siddiq, what is the specific consideration by changing the core configuration as well as the size also look like pancake core type in comparing to previous core configuration, which was tall and balanced geometry type core reactor. Volume is still same, new or old one. So Lars, I think this is your...
Yeah. So what we found was that we could not buy graphite the size we wanted. So we had to make the core shorter than we would naturally choose in order to accommodate what we could purchase in terms of graphite. We have avoided having seams between pieces of graphite in the center of the core because that could lead to salt that's trapped in the seam. And then you would get a concentrated heat source without the coolant flowing by it. And we want to have, if it's when the salt fissions, we want it to keep flowing because that's where 90% of the heat is going. If you stop the flow of the salt and it's still fissioning, it's going to heat up very rapidly. And it has to get cooled by conducting the heat through the graphite, which is a much less effective heat removal system than the salt flowing. So we don't want to have seams in the center of the graphite, in the center of the core. So that limits us to the height that we can have. We made the reactor larger diameter in order to accommodate it. The aspect ratio, I think, is like 1.6 to 1, which I'd rather have a 1-to-1 aspect ratio. That would be a preferred choice, but we're still within a reasonable range. And yes, the volume is roughly the same as the old one. That dictates the graphite lifetime.
All right, so I hope that answered Dr. Siddiq. So the next one, Professor Juarez, about the freeze valve design is exactly the same has been used in Oak Ridge. What is the influence of the fuel cell type since MSRE uses FLIBE and ThorCon use NABE? Is this last? I think this is your thing.
Yeah, so NABE has a slightly higher melting point than FLIBE. Not a whole lot, but a little bit. So we will have to adjust the temperatures, but otherwise they're going to be very similar. We will have to build a freeze valve and do component tests on it to find the right temperature settings. But otherwise, I think it's going to be basically the same.
All right. So next one's for Dr. Aziz from Bapeten. How does the flow behavior change due to the graphite deformation, shrinking, expanding as the result of possible high energy neutron influence? Manu?
Yeah, in the gaps between logs, when graphite shrinks, the space for the flow increases, and so locally the pressure drop decreases, and the flow rate in that channel with respect to the rest of the core on average increase. So there is a redistribution, a small redistribution of the flow rate throughout the core due to the change of the thickness of the gaps between logs due to the shrinking of the logs. It has to be taken into account. It does not have a huge impact. The flow distribution is controlled by both accurate gap sizing and localized pressure drop or orification in the plates below or above the logs. So that has taken into account that correctly. So as you state that it changed the flow distribution, it does not have a huge impact though.
All right, you want to add that, Lars, or is that sufficient?
That's mostly sufficient. We have flow both in the gaps and in the holes. The holes don't change size very much. So we have to balance when the gaps get larger, the salt coming out of the gaps goes up in temperature a little, and the pressure drop in the whole core drops down. So the flow in the holes goes down. But you get mixing at the top to balance out the slight changes in temperature we're talking about changes in temperature on the order of 5 to 10 degrees.
All right, still from the same person, Dr. Aziz. He said, flipping, I missed the void reactivity coefficients and control rod shutdown margin from your talks. So Lars or Manu here? Manu?
Sure. The void reactivity is, well, namely the salt expansion coefficient. Being an under-moderated reactor, we do have locally a positive void reactivity in the sense that if we introduce a small reduction of fuel density, there can be an increase in reactivity. This increase of reactivity, though, is overcompensated by the negative introduction of reactivity due to the salt heating. So if we are discussing by just salt expansion, the overall effect, so due to thermal expansion, the overall effect is severely negative, and the overall temperature coefficient of the salt is negative. Moreover, if we are discussing by introduction of void in the form of bubbles, this is first of all unlikely due to the specific configuration of the reactor that prevents the introduction of large fraction of voids. And after that, if there is a large insertion of local void, that goes back to being a negative effect on the reactivity. So the only case in which we have a positive introduction of reactivity is by having a small distributed insertion of void. So this is, on one hand, a small effect compared to the negative reactivity feedback related to temperature, and highly unlikely due to the unlikely events of having a distributed distribution, sudden introduction of bubbles from there. But Lars, if you want to take this further.
The other thing I'd point out is void coefficient of reactivity is a very important factor for a water-cooled reactor, where if you started picking up reactivity, you go hotter, then you boil more water, you create more voids, you get hotter still, and you get this whole positive feedback system. So that's a big concern for a water reactor, that you have a negative void coefficient. We're a salt reactor. We don't get boiling of the salt. That simply isn't, we got 700 degrees C margin. That is not something that will ever happen. So our bubbles are gas bubbles. There is no positive feedback system that's going to make more gas bubbles because it's getting hotter. So we don't have the positive feedback system. The voids do introduce some noise in the power level. So we'll see fluctuation in noise because of the bubbles, either if they're being introduced or if they're being compressed or expanded. It goes both ways. So a large negative void coefficient would also create more noise. Just what would happen when the bubbles leave or when they get compressed. So we would prefer to have a small void reactivity coefficient, whether it's positive or negative, either way, doesn't matter.
And about the control rod shutdown margin, I think hasn't been answered, Lars.
So the control rods, we are targeting to have around 2,000 PCM on 3 control rods when they're all inserted, between 2,000 and 3,000 PCM. So that's your margin. Remember, this reactor doesn't have burnable poisons, and it doesn't use the control rods for trim. So that is the value of the worth of the shutdown rods themselves is the margin we have.
All right. So the next one from Helen. What is the purpose of using thorium-232 together with uranium-235? How is the distribution conversion ratio value for 4 years burn time? Want to pick this up?
Yeah, there's a couple of reasons for preferring thorium. In a thermal reactor, uranium-233 is a better fuel than uranium-235 because it fissions at a higher percentage. So we'd prefer it for that reason. Second, we get a second shot at it for the part that doesn't fission at 233, becomes uranium-234 and then becomes uranium-235, which was another fission. So we get two shots at it that way. If it was started from uranium-235, then we would go through a long series before you get up to 239 to fission again. What was the next question? What does it do to the conversion ratio?
Yeah, for the 4 years burning time.
Yeah, I think the more important question would be, if we have no thorium in there, then we have more uranium in there. And we need to keep the uranium fraction or the uranium is our redox balance. So it's our buffer, chemical buffer, and we want to keep the ratio of UF3 to UF4 at about 1 to 60. So if you have no thorium in there, you've got a lot more uranium, maybe 5 times as much uranium. And that means I start out with 0.2% or so of trifluorides just from the uranium, which means my fuel lifetime is shorter. It also means that the fertile that's being converted, instead of going to uranium-233, the fertile I'm converting makes plutonium-239, which is a much less effective fuel for a thermal reactor, as you get about a 60% fission rate on plutonium-239 versus 90% for uranium-233. I haven't actually calculated the conversion ratio when we're running on pure uranium. We can run on pure uranium, and that's very beneficial because it may be a while before we get high assay LEU to be able to burn. But definitely the baseline plan is that we're using a mix of thorium and uranium.
Okay, I hope that's answered. So the next one from Professor Sarif from Batan. On slide number 26, it is shown that the production of xenon 135 after reactor shutdown reaching its peak in 6 hours. Am I right? That's a question. If that's true, why is it faster than typical solid fuel reactor, i.e. about 11 hours? So Manu, please.
Yeah, in solid fuel reactor, after a shutdown or after a sudden reduction in power, the main term that leads to the removal of xenon is the decay. So the path is the uranium to the iodine decaying into xenon, and the xenon being removed by, again, decay. In our case, though, the main path for the removal of the xenon is through the ether tank. And we have two assumptions in this specific case, as a fast effective removal rate or a medium effective removal case. And you're right, in the medium case, the peak happens within the 6 hours after the change in power. In a fast removal rate case, it happens even before. It is also to say that the removal rate is not a removal rate in the sense that I'm removing a given amount of xenon per time interval. I'm removing a fraction of xenon. So if I double the xenon and I keep constant the removal through the same exposure of salt to the gas, or the same rate of salt through the gas-salt interface, I will doubling my removal rate. All this together makes the peak happening much faster and being much, much lower than solid fuel reactor. I don't know if this makes sense to you. So
I'd
the
like
main
to,
oh, please, Lars, go ahead.
If you completely stopped the flow, so when you stop the flow, there's no flow going to the spray ring in the header tank. We are not removing any xenon in the header tank. And in that case, it's the same. It's somewhere between 10 and 11 hours that you hit your peak.
Okay, so it is because you're removing the xenon in the header track, so it become faster. Is that the answer?
Yeah.
Okay, very good. All right, so question from Dedi Setiawan. How much temperature of the drain tank and graphite can still keep fission product not released? For instance, the pebble bed rhizo particle can still keep the fission product until 1600 C. Does MSR need containment? Okay, who answered this?
I'll take it. At about 1200 C, we'd expect to see some cesium fluoride coming off, as well as some beryllium fluoride. So yes, we still have containment. The first level of containment is the can. And then the can is inside a silo cavity. And the silo cavity is inside the ThorCon aisle. So the can and silo cavity are inerted spaces with no air conditioning or venting. So those spaces should be almost completely gas tight. The ThorCon aisle does have people in it, so you have an air conditioning system that needs to be switched from external air to recirculating. But we do have containment. Containment for the first level is the can is steel that's at about 350 degrees C and under no pressure or under 1 bar of pressure. The silo cavity is basically under very slightly negative pressure and is steel that's at about 100 degrees C. And then the hull is got steel and then 3 meters of concrete and then steel. So pretty strong containment.
All right, so that's, I guess that's very clear. So the next one from Almanzo, he said, "Got it. I guess I found it interesting. There are several deterministic codes to do neutronics analysis too. I think OpenFOAM can be used to do multiphysics analysis too. Maybe this can help in saving runtime for the simulation MSR. Great lecture. Thank you." Maybe Manu, maybe you want to comment?
That's a very good point. OpenFOAM can by itself, without external coupling, being used as a deterministic solver. I've developed in the past 10 years, so unfortunately a lot of deterministic solvers. In the specific case of the ThorCon reactor, the local heterogeneity effect and the reflector effects, along with the fact that the gap size change from one log to the other, makes the adoption of deterministic, especially diffusion and ascent solver, less accurate and Monte Carlo preferable. Overall, the CPU cost is affordable, I would say. But yes, there are deterministic solvers.
Right.
If I could continue with that.
Right.
So we have worked with Argonne National Labs. They have some deterministic solvers. And after some adjustment, we got results that were within a couple % of each other. But in my opinion, you have confidence in the Monte Carlo effect. In the deterministic ones, you'd always know that you've got to calibrate it and check to be sure. So our runs, for a typical run that does burn up over an 8-year period, it takes about 20 minutes on a 16 core machine. So it is time, but it's not particularly onerous. We have used that to set up point kinetic models of the whole system. Manu's team has developed one of those. Stefan Kvist's team has developed a second one that we use for checking out dynamic behavior of the whole system.
All right, I have a follow-up question on that, maybe to Manu. If, for example, Bapeten would eventually evaluate ThorCon design, what software do you suggest, other than the regular one that Bapeten would use? Any recommendation that may be specific to MSR? So please, Manu.
As you know, the legacy software are not perfectly suited to molten salt reactor, but all over the world, safety authorities are adapting to the evolving panorama of molten salt reactor companies breeding new reactor types. In US, it is led by Argonne with the same code, and at TRSN in France, for example, people are using OpenFOAM. So there are a lot of tools that with minor modification are made available nowadays. So if you have any specific question on a specific set of tools, I will be happy to answer. So let me just send me an email on specific tools you are evaluating, and I can get the help of my colleagues at Politecnico di Milano, because a lot of tools are being recently used, from the Milano Modelica up to more old code in the relap style that have been tweaked to work with molten salt reactor. So I would say there is no legacy tool adapt to molten salt reactor, but there are tens of tools adapted recently to molten salt reactor. Send me an email with the specific tools you have in mind, and I can point to their past use in molten salt environment.
Manu, maybe I can ask you a favor. If maybe instead of maybe you can send me an email or sort of like list of the tools that you would recommend, and what are the plus and minuses, and short description of the tools. What does it do?
Yeah, are you looking at neutronics and core analysis, or system analysis?
The whole thing, because eventually, because eventually Bapeten need to analyze, right? So maybe you have experience, and what are not the legacy tools, right, specific to MSR.
Are you bounded to NEA or RSIC released code?
Yeah. Okay. Whatever you think that what you recommend, I think, right? So I think if we don't have any more question, I think. So I'd like to give the last statement to Lars and Manu, closing statement. Lars, Manu? Lars first.
So I leave Lars taking care of this.
Okay, Lars.
Okay. Well, thank you very much, everybody, for your attention and raft of questions. We welcome more questions. I would very much prefer to have you ask a question, and if we stumped, give us a chance to try to figure it out before we build something. Don't want to have you tell us after we build something that, yeah, I thought about that and wondered about it. So please feel free to ask questions. I would anticipate that we'll work with some of the people here to be sure that they get cleared for 810, so that we can be more explicit with the interior of the core, and you can run your own simulations. As of this moment, we are still working with the graphite vendors to settle exactly what they can and can't do. So there's some adjustments, and these all have to do with how do we mechanically attach the graphite and deal with the difference between the graphite and steel's thermal coefficient of temperature expansion. So they're not focused on the neutronics. The neutronics seems to work pretty stably across a variety of core configurations, but it's how to be sure we get things anchored properly using graphite that actually can be manufactured. So look forward to working with you more.
Okay. Lars, don't go away first. We still have picture taken usually, right? All right, Kun, last words to you.
I don't have anything to add. Just to remind everybody that next Friday, we're going to have our week 4 workshop. We're going to talk about the operation and the balance of the plant. I'll see you there.
Okay. Pak Tagor, could you please conclude the session, the resume of the session, please?
Thank you, Pak Bob. Okay, wait a moment. Okay. I just want to share okay.
Okay, this is the summary, everybody.
Yeah, I just make a summary for this training based on the material and also from Dr. Manu and Dr. Lars and some from question and answer. I think the point number one, we have to say that the important components in the reactor can has been revised, including the reactor pod and primary heat exchanger. The reactor pod uses the graphite as a moderator and NABE as the fuel. And the pressures is about 3 bars with the inlet and outlet temperatures are 565 C and 704 C. And the lifetime of reactor can is 4 years because limitation of graphite moderator in the high neutron energy radiation and high temperature. Graphite will shrink and then swells. Number 4, the reactor core has negative reactivity coefficient from fuel salt temperature and the graphite temperatures. The reactor will be shut down by rod shutdown, then shutdown rod, then the fuel is drained to the fuel drain tank FDT. Drain tank purpose is to remove the decay heat fully passively. And then goes to number 6. I think a couple neutronic with thermohydraulic or CFD model. In the case of Milano Multiphysics, they use Serpent and OpenFOAM. It is implemented to fully describe the reactivity as a function of the free surface height of fuel salt. The circulation time in the primary system is about 10 to 15 seconds, and full draining takes about 786 seconds, or is about 13.1 minutes. The subcriticality condition is fulfilled for the makeup tanks and then FDT when those are flooded by water. Freeze valve is passive system. FDT is cooled by natural circulation of cold wall. Some drain tanks have been calculated as well as the xenon behavior due to the power operation or the effectiveness of gas cooling tanks. And number 13, the decay heat is deposited in the graphite inside the core. For example, in the square block geometry, approximately 40% of the decay heat is released in the graphite. The principle of fuel management in the ThorCon design is also presented, and the shutdown margin of the roads is about 2,000 till 3,000 PCMs. That
Okay,
is summarized from me.
Is that correct, Lars? Any correction, Manu, of the resume?
No, that looked right.
Okay, very good. So that's correct. Manu?
Sure. Lars approves that. I have nothing to say, of course.
Okay. All right. So close the share screen, Patagor. It is time for photo session. Okay, guys. Show up your face. AJF, are you there?
Yes, Pak Bob.
Okay. So picture time, everybody. Look, smile. Yes.
Okay. 1, 2, 3.
Yes.
And the second slide. 1, 2, 3. Okay.
Okay. Thank you very much. Terima kasih, everybody. Thank you, Lars, Kun, Manu.
you.
Thank you, everybody semuanya.
Bye-bye.
Bye-bye.
Bye.
Until next week.
Thank you.
Bye-bye
Thank you.
now.
Thank you
Thank you very much.
Lars, Manu.
Thank you. Next week.
Thank you very much.
Thank you.